Thanks, Adway. Good morning from Pune to all of you, all in-person and online participants. We have as many online participants as much as we have the in-person as well. I also, ask you to be mindful about your microphone. Keep your microphone off while we are having the lecture. We have a Q&A session at the end of the lecture. And Dr. Gokhan is joining from the US. Time over there is 9:30 Sunday evening, so be mindful about that as well. So to introduce Gokhan, Dr. Gokhan Danabasoglu is a senior scientist and the section head of oceanography section of the Climate and Global Dynamics Laboratory at the NSF, that's the National Science Foundation, at NCAR, National Center for Atmospheric Research in Boulder, Colorado in USA. He served as the chief scientist of the Community Earth System model. Now, this is the most probably relevant part for our workshop summer school here. He did that during 2018 to recent 2023. Gokhan is an expert in ocean and climate and earth system modeling. He has primarily focused on understanding the role of oceans in Earth's climate system and computational modeling of the ocean as well. His specific areas of research include investigations of mechanisms, prediction, and impacts of interannual to multi-decadal timescale, climate variability, which is particularly associated with the Atlantic meridional overturning circulation. He has also focused on high-resolution Earth system modeling. He is a recipient of the 2009 CESM Distinguished Achievement Award. He has served on many national and international panels. I work along with him in CLIWAR. He has been a chair of the US CLIWAR, a mock science team, and currently he is the co-chair of the International CLIWAR program. And he has authored and co-authored over 200 publications. He received his MS and PhD in aerospace engineering sciences from the University of Colorado Boulder. He's originally from Turkey. He had his undergraduate degree in mechanical engineering from Bosporus University in Istanbul. So Gokhan will be giving three-part lecture series today, tomorrow, and day after tomorrow. I invite you all to this extensive lecture starting with an introduction to Earth system modeling via the community Earth system model. Many of you might already know or might be using the community Earth system model. I'm not taking much time. We have a 10-minute Q&A session at the end of this lecture. So over to you, Gokhan. Thank you. Thank you for being here.
Yeah, thank you for inviting me to participate. As I was saying at the beginning, I wanted to be there in person, but I couldn't get an Indian visa, so I'm here trying to participate remotely. And I know that it's not the same remote participation, but if you have any questions that we cannot fit here, please feel free to contact me via email. So I'll be happy to answer those questions. So as Roxy indicated, I'll be providing an introduction to Earth system modeling, and that'll be primarily based on the Community Earth System model, that's CESM. And oops, I need to advance it. Okay, so just this is a brief outline of the presentation. I'll be talking about global Earth system modeling, focusing on why we use them. I'll be talking about their complexities, ensemble size, and resolution considerations. It's essentially a trade-off between complexity, ensemble size, and resolution regarding your science goals and computational costs. I'll provide a brief introduction to CESM, talk about its governance, capabilities, and main strengths. Then I'll be showing some examples of challenges and application areas of Earth system models using CESM as an example. I'll briefly talk about high-resolution Earth system modeling. I'll, towards the end, summarize our machine learning efforts. This is a rather new area for us. I'm not really an expert in machine learning, but we are learning as we go, as we incorporate new machine learning approaches into CESM. And I'll conclude this particular presentation or lecture with a list of sort of, in my view, some challenges and opportunities in Earth system modeling looking ahead or going forward. So I'll start with sort of an introduction to global Earth system modeling. We use global Earth system models as a virtual laboratory for experimentation. Some of the general purposes for use areas include providing scientific and mechanistic understanding of past observed events and changes. We use them to simulate recent past, present, and future climate states and their impacts. These are essentially forward-looking, long-time scale projections. We use scenarios to do these things. We use the global Earth system models to study climate variability and also for making subseasonal to multi-decadal Earth system predictions. And for those of you who are not familiar with what the differences are between projections and predictions, projections are uninitialized simulations. They are primarily essentially subject to forcing fields or forcing data sets. Predictions actually, in contrast, represent initialized Earth system model simulations. They essentially try to initialize the system with the present state, let's say, of the climate, and then we try to go forward in time and try to provide forecasts, whether it's just like weather forecasts, subseasonal to multi-decadal predictions. And in general, the overarching goal is to provide actionable, societally relevant information for the world, essentially, not just for the US, but all the nations. So on the right side, I have a sort of animation showing from one of our high-resolution simulations. The colors are the sea surface temperatures, and the white areas are showing the sea ice extent. And you occasionally see sort of typhoon showing up and their signatures in the sea surface temperature fields with their cold wave. I think you have seen one of them showing. It should show up pretty soon here. Yep, you saw one right there. Okay, so I actually, if you're interested in sort of looking more into the history of Earth system modeling, we had a recent manuscript published. This is actually, well, about 5 years ago, 2019. Dave Rendell was the lead author, and we summarized sort of the history of Earth system modeling. All the components are included here: atmosphere, sea ice, ocean, land modeling. And the picture here is showing I think this is the first computer that was used. It's the electronic numerical integrator and computer used for forecasting purposes. This is during the Second World War. And you can see it's filling the whole room. And if you're interested in this is recorded, so you can check the DOI number, and it's an interesting reading if you're interested in. So global Earth system models, as you may know, use physical equations to simulate key fields and processes in the component models: atmosphere, ocean, land, sea ice, land ice, and we have the runoff model as well, and the biogeochemistry. And these equations are discretized on a sphere, as shown here on the upper right panel. We have the horizontal grid, vertical grid, and as you can see, many of these and then these are the schematic is showing various processes that we are trying to essentially represent or include in an Earth system model. However, many of these processes remain below the grid resolution, and since they are not being resolved, their impacts somehow need to be included in an Earth system model. And for that purpose, we tend to use parameterizations. And these parameterizations build on our understanding of processes from observations or highly detailed models. And these models could be process models or large eddy simulations, just to give two examples. And as I'll touch upon towards the end of this presentation, this is where the machine learning or AI techniques can be used. And many of the efforts that are going on are trying to essentially replace existing model parameterizations such as mesoscale eddy mixing in the ocean or some of the cloud parameterizations using ML AI techniques to essentially replace them. So just to give you an idea about three sort of competing things in Earth system modeling. One is the model complexity, the other one is the ensemble size, and the third one is the resolution. So when you have a science problem at hand, you need to essentially consider your computer resources, your science goals, and try to figure out what model complexity, what ensemble size, and what resolution you would like to use to answer or to accomplish your science goals. The upper two schematics are showing sort of increasing model complexity as a function of time. And when sort of Earth system modeling at that time, pretty much just the atmospheric component, and it was sort of, well, not even coupled to an ocean model. It was primarily the atmospheric model, used to be called sort of the climate system. It started in sort of mid 1960s, and you can see that throughout time, more components got added, including ocean, sea ice sheets or land ice, and many components also, many additional parts such as biogeochemistry, interactive chemistry, they got added continuously. And the upper right panel is also showing that not only we ended up adding more components into the Earth system models, but we increased their complexity in each of the component models. So this is one thing that we need to keep in mind. Sometimes you don't need all the complexity that is included in an Earth system model. The lower left panel is showing importance of ensemble size, and I'll show another example of that thing on one of the next slides. If you are interested in essentially internal variability of the system, then even if you initialize it from a common point here, which is right here, then small perturbations of the system will produce quite different results as you integrate it in time. So again, how many ensemble members you would like to use in a simulation for a given problem will depend upon your science question. And then finally, the third component of these competing sort of effects is the resolution. As you increase the resolution further and further, you get more details, and perhaps you don't need some of the parameterizations that are used in lower resolution models, but that comes at a cost as well. So you need to consider all these aspects. This is another way of showing this thing. This is essentially created by our own institution, UCAR. And it is, again, the upper part is showing model complexity as a function of time. And you can see that more components got added. In 1970s, land and ocean components, 80s, sea ice got added, and then so on. And the lower panel is showing the computing, essentially computational speed in teraflops. And I added the sort of the red numbers here just to give you a flavor of what the model resolutions were or have been throughout time. Initial model resolutions were of the order of 500 kilometers. These are all in kilometers. And as we come towards sort of the present day, we tend to have more models or Earth system simulations that use order 100 down to maybe 10 kilometers. And then you probably heard about kilometer scale modeling. Those models tend to use order kilometer resolution for model components, but simply we don't have the computers to run them long enough. They tend to be really short simulations. And not only essentially we need to be mindful of the computer resources, but we need to also be mindful of data storage. As we go to higher and higher resolution, we get more and more output. how do you store those data sets, and more importantly, how do you serve those data sets to the community. So all of these need to be considered carefully. So need for ensemble simulations, what I'm showing here is from our CSM2 large ensembles, we have 100 ensemble members. And what is shown here is the sea surface temperature trends for the 1920-2014 period. These are in degrees Celsius. So these are roughly 100-year, let's say, trends. The top two, upper left, these are estimates from ERSST and Hadley SST. So you can see, I mean, even the observational estimates, observational-based estimates are showing some differences. And the remaining plots show these trends from roughly, I believe, 50 ensemble members, half of the ensemble members. So you can see that even if we are essentially forcing these things using the same historical forcing data sets, the trends in sea surface temperatures it can be quite different. For example, in the Pacific Ocean, this ensemble member is showing a cooling trend, yet the next door, this neighbor, is showing actually a warming trend. And similarly, you may have heard of this warming hole sort of appearing in the Atlantic basin in the North Atlantic. This ensemble member, for example, shows a cooling trend, which warming hole means that there's a cooling trend among sort of surrounded by warming trends. And yet, if you look at this ensemble member, you do not see a warming trend. So this is actually important to get a handle on the internal variability of the Earth system models. And resolution, of course. So this is from the atmospheric side. In the atmospheric modeling, pretty much clouds are everything. And just to give you an idea, this is the typical sort of 100-kilometer sort of box grid resolution that's used in the atmosphere. And then different clouds are shown here. So clearly all of those clouds are below the grid scale and their impacts somehow need to be parameterized. In the land surface area, land surface types are quite different and they're quite complicated and they need to be parameterized. Their impacts somehow need to be included. And this is an example from the sea ice sort of observations. These length scales are given here. So you can see that there are ridges, and this is like 10 meters here. Leads, this is 500-meter length scale here. And then you can see various sea ice features here. There's open ocean here, tiny fraction. Melt ponds are given here. So this is actually over a 440-meter length scale here. And all of these, again, with the sea ice grid order 100 kilometer used in workhorse models, all of these impacts need to be included to the extent possible in simulations. And this is showing from the atmospheric modeling, the sort of how the bottom topography is represented as a function of model resolution. The upper panel is showing, or the upper row is from a standard horizontal resolution, sort of couple model intercomparison project type or intergovernmental panel on climate change class climate simulations with resolutions of order 100 kilometers. And this is the continental United States, and these are the Rockies. So you can see that there's not much detail. So if you go to somewhat higher resolution, this is atmospheric model is now 25 kilometers. This is from one of our simulations. You tend to get a better handle on topography. And then this is sort of now we are talking about ultra high, what I call ultra high resolution, where the horizontal resolution is of the order of 3 to 4 kilometers. You can clearly see that you are actually doing a much better job of representing topography. And these are all, I mean, some of the, if you are interested in hydrological cycle, for example, over the continental United States, or particularly over the Rockies, then you need to have relatively high resolution to be able to have a better representation of the hydrological cycle and along with the sort of river flows, river runoff. So, and then this is an example from one of our ocean simulations to give you an idea about how the length scale of the sort of eddies in the ocean model. In the oceans, mesoscale eddies represent with the length scales of order, well, depends on the Rossby deformation radius, but in general, with order resolutions of with length scales of order 100 kilometers, in order to be able to resolve them, you need definitely more grid points over that length scale. And that those features are shown here. Essentially, this is the crochet extension. You can see various mesoscale eddy features, or right here, and particularly along the Southern Ocean. These are representing the most energetic component of the oceans. I'm pretty sure you have seen a version of this particular plot or schematic. What is shown here is on the vertical axis is the time scale from 0.1 second all the way to 10,000 years. And the x-axis is the spatial scale from order 1 millimeter all the way to 10 to 5, 10 to 5 kilometers. And various sort of processes or climate phenomena are included in the plot. So if your resolution is of the order of, let's say, 3 degrees, you can essentially sort of resolve in quotes. You may not be fully resolving these phenomena, but mostly you may, for example, climate change. You may be essentially representing all these time scales and with these length scales that's sort of roughly indicated by the red box here. You can get order 100 to 10,000 years simulation per day, which is very fast. And this can be used for paleoclimate applications if you're interested in order many thousands of years. Workhorse models that are used in IPCC or CMIP type simulations, they tend to be order 1 degree or 100 kilometers, and you end up resolving these sort of phenomena. And you can get order 10 to 100 years per day in your simulations, which is reasonable. And if your resolution is 10th of a degree, which is order 10 kilometers, then you are essentially starting to resolve more spatial scales and include more phenomena, and your integration length is less than 10 years. And with kilometer scale modeling, this is sort of relatively new. You are again increasing your spatial sort of scale, but your integration length is going to be a lot shorter. Depending upon the machine, depending upon how your optimization is done, you can get order maybe half a year per day, or some of the centers are actually running maybe order 1 year per day. But you can clearly see that you cannot do many experiments with this kilometer scale modeling. So I'll just now switch to CSM a little bit and then talk about briefly its governance, capabilities, and main strengths. So CSM, Community Earth System Model, is one such global Earth system model. It's an open source community model available via GitHub. And if you're interested in finding our latest and maybe not necessarily greatest version of the model, you can just go to GitHub and search for CSM. You'll get there. And it has a coupler. There we have the atmospheric component, sea ice, land ice, ocean, surface waves, river runoff, and land components. Both the land and the ocean, they have their biogeochemistry components. And the forcings are provided through the atmospheric model at the top of the model. And these include greenhouse gases, anthropogenic aerosols, volcanic eruptions. That's actually embedded in the atmospheric component. And you can represent the solar variability. CSM is as I said, I was trying to stress, is a community model. So it's a bottom-up modeling approach. We have 12 working groups, and they are given here. Some of them are model development working groups, such as the ocean model development, ocean model working group. We have the atmosphere model working group. You can see the land model, land ice, biogeochemistry, chemistry, climate. These are all development panels. But we have also some analysis panels, such as the Earth system prediction and climate variability and change working groups. We have over 30 years of model development and applications experience. And its governance, as I said, is a community-based governance structure. Each working group has an internal and external co-chair. We have a CSM scientific steering committee, and at the top we have an advisory board. It can be used for a range of climate simulations or Earth system simulations. And it is a single code base which can be run on a desktop, and you can use it in a single column mode or in a coarse resolution environment. And it can be used for example, physics development or maybe coarse resolution paleoclimate applications. It can be used on a small cluster. Again, it can be used for low resolution. It can be, I don't know, 2 degrees. And again, paleoclimate applications is a prime example of that. And it can be used at a university setting for research or classroom purposes. And finally, at the high end, you can use it on various supercomputers at medium, high, or ultra high resolutions. And we tend to use this kind of sort of setup for couple model intercomparison project participation, running large ensembles, or various new scientific applications. It is containerized. That means it can be run on cloud in a container. So various configurations are available. And all of these are accessible through the CSM website. We do have workshops and winter working group meetings. Indeed, just a few weeks ago, we had our annual workshop. And actually tomorrow, this coming week, we will be having our tutorial. Every year, we have annual tutorials. They are actually, they happen at NCAR in Boulder with participation of roughly 80 to 100 students. We also run tutorials at AMS and AGU meetings. These are shorter, half a day to 1 day tutorials. If you're interested in learning more about CESM, you can, as I said, go to our website. You can learn more about who we are, what we offer. We have a forum, and if you have any questions about CESM, its components, model, how to set up the model, certain science questions, you can essentially post them here, and either us or somebody from the community will answer those questions. And again, all of our sort of data sets, our policies, availability of the data sets are all available through these websites. This is where we run our simulations. This is our NCAR Wyoming Supercomputer Center. It's in the state of Wyoming. It's about 90 miles north of Boulder. This is our older machine. Cheyenne is no longer available, actually. It has been recently replaced by a system, Drecho. It is roughly 20 petaflops of supercomputer power. Just to give you an idea about how much of the computer we use for our 1 degree CSM2 simulations, we run it usually on 4300 processors. It takes about 3500 CPU hours per year, and we can get about 30 simulated years per day. And this is essentially with usual standard I/O. This is the sort of low top model version in the atmosphere. If we go to higher top version, that requires about 23,000 CPU hours, and we can run it on 3780 processors. And at our high resolution CSM1 model costs about 50 to 100,000 CPU hours per year, and that depends upon how many fields we get as output, and that model throughput changes anywhere from 2 to 6 years per day, just to give you some idea. Okay, so what are some of the examples of challenges in Earth system modeling and application areas? And again, I'll show you this thing through CESM as an example, as a base. So one of our, and in Earth system modeling, even though, I mean, there are many, many challenges. You can essentially develop your component models separately and you bring them together at various stages throughout the process. And even if you get the best results in your component-only simulations, when you couple all the components together, nothing is guaranteed because there are so many interactions going on and there are so many biases, compensating biases, and they may result in weird structures. So one example that we, for example, encountered during our CSM2 development is this green line here. What is shown here is the temperature anomaly during the historical period. And ideally, you want your model to produce the observational time series, which are shown by the gray and black lines here. But in our simulations, we ended up getting with what is shown by this light green line here. And that's clearly not matching observations. So we went back to the model, checked everything, and then we found problems with aerosol cloud interactions. And once some of the things that have been corrected or were corrected, then you end up getting essentially this red line here. So that was one of the sort of challenges. Another challenge that we are still struggling with in CSM3 is freezing of the Labrador Sea. What is shown here is the sea ice extent in the Arctic in the northern hemisphere. This is sort of what you would like to get, the panel on the left side. But in many of our simulations in CSM2 and now in CSM3, we end up getting this excessive Labrador Sea ice formation, and that has adverse impacts in the model overturning circulations, temperature distributions, and all kinds of biases. So this is one of the major challenges, and many groups actually have similar problems with the Labrador Sea. Just to give you an idea about some of the how some of the persistent biases still are present. Well, that's why they're called persistent, I guess. What is shown on the left side is the sea surface temperature. On the right side is the precipitation. In each case, the upper panels show some kind of observational estimate of the field, sea surface temperature and precipitation, respectively. If you look at the sea surface temperature on the left side, these are the actual fields from CSM2 low top, CSM2 high top, and CSM1. That's our previous version. And then these are the differences from these observational based estimate. You can see that one of our persistent biases is these warm biases of the west coast of continents, and they are still significantly there. You can see incorrect separation of the Gulf Stream here. We end up essentially getting a dipole structure, warm and cold bias. So one of my challenges for machine learning applications is rather than producing incremental advances, I would like machine learning AI techniques essentially to be able to address these persistent biases. And these are just two examples from the sea surface temperature distributions. In precipitation, again, low top, high top, and CSM1 simulations are shown here. A persistent bias is what's called as double ITCZ. You can see that in the observational based estimate, we have a single sort of intertropical convergence zone, and there's South Pacific intertropical South Pacific convergence zone here. And in the modeling world, they tend to be two zonal, and then we end up sort of a double ITCZ structure. So these are some of the persistent biases in coupled Earth system modeling. Some application areas, as I said, one of them is actually growing significantly is Earth system predictions across time scales. As I tried to identify initially, these are initialized predictions. So you start with some known state to the extent possible of the climate system, and you run it forward. And the idea is to get subseasonal to multi-decadal predictions. And then these are needed for various societal applications, and the results can be provided to various stakeholders and decision makers. Another application area that is actually quite interesting, and I think this is what I find at least interesting, is that in the sort of 1991, 1992 timeframe, South Africa actually was hit by a drought, really severe drought condition. And this is shown this is from New York Times in March 1992. And we ran CSM2 simulations to sort of understand what the causes of this drought was. And it turns out that the 1991 eruption of Mount Pinatubo actually was the reason for this drought. So what we did is we have our regular simulation, which is the control case with the volcanic eruption included. Then we ran several ensemble members in which we simply eliminated the volcanic eruptions. And when you take the difference, you can see a clear signal in over South Africa that without the volcanoes, there is no essential drought condition. This is essentially showing the impacts of volcanic eruption creating, this is the difference, so that you need to see a negative signal here to show that the volcanic eruptions are actually creating the drought conditions over South Africa. We do have, as I said, in the Earth system modeling, we include biogeochemistry, and this is in CSM. We use MARBLE, that's called Marine, that's a short acronym for Marine Biogeochemistry Library. We have two zooplankton types, microzooplankton and mesozooplankton. We are actually in the process of coupling it to a fish model. That's the feisty fish model in an online manner. We can run it offline using the output from biogeochemistry model, specifically providing microzooplankton and mesozooplankton data sets. We can run it offline, but we are in the process of essentially including this fish model in a prognostic way within the CESM biogeochemistry component. Okay, so we also have tools. We have developed recently tools, GUI-based, as the graphical user interface tools to support CSM setup. And you can essentially use this GUI-based tool. You can just click on with your mouse certain sort of atmospheric components, and it will essentially tell you what's available for each setup and what is not available. The compatibilities are going to be checked, and then it will create certain data sets for you or all the data sets needed for a particular configuration. So I don't want to get into too much detail here, but again, if you go to the CSM website and if you essentially search for a simpler model or GUI-based interface, you'll essentially get a hold of this particular nice feature, easy for model setup. Okay, high resolution Earth system modeling. So as part of our several, we are with collaborations with particularly with Texas A&M University, we have created quite an extensive set of high resolution simulations with CESM. This is using an older version of the model simply because we had more experience and it was ready to go when we started this project now about 10 years ago. These are actually obtained using 10th of a degree ocean and sea ice and quarter degree atmosphere and land models. The simulations that we have essentially completed are listed here. The ones that are in green are actually available to the community. And if you're interested in using these high resolution simulations, for example, for training of ML AI techniques, you can essentially take a look at our data sets. We are still extending our decadal prediction simulations by adding more years and also more initialization twice per year. They are not fully available yet. And this is just a movie showing sort of eye candy, again, from these simulations. This is for year 2100. It is, in this case, showing the specific humidity. And it'll also switch to sea surface temperature and atmospheric rivers. That should be coming up soon. I can fast forward. Whoops. So you can start seeing actually landfalling atmospheric rivers over here. And in the background, you can see the sea surface temperature data set. Okay. So another thing that we are actually analyzing these simulations quite extensively. And one of the things that we are looking at tropical cyclones and how they would change in the future. These panels are showing on the left observations for tropical cyclones as a function of their category. The middle panel is showing CSM high-res simulation, and then the low-res is on the right side. I mean, this is not surprising. We get better distribution of tropical cyclones in high-res, but note that we are not capturing the higher categories, and our latitudinal extent is way too much compared to observations. So there is still work to be done. In our future simulations, future scenario simulations, now we can essentially look at how the TCs will be changing in the future. And this is showing an example of future 30 years minus 1950 to 1980 period. These are number per year. So our simulations are indicating that the tropical cyclone activity will decrease, for example, in the Atlantic as well as in the southern Indian Ocean. But over the continental sort of Indian subcontinent, there's actually an increase in the tropical cyclones and decrease further south. And if you look at, for example, associated TC-induced rainfall rates, you can see that even if, for example, in the Atlantic basin, the tropical cyclones are decreasing in number, their precipitation rates are increasing. So this is an interesting feature. They are becoming essentially more intense. There are you can do variable grid resolution in the atmospheric model. This is with spectral element dynamical core. It's using a cube sphere approach. We have various versions of this model in which enhanced or increased grid resolution is used, for example, over Arctic. And there is actually one over Himalayas region. This is being used for, I believe, air pollution studies. I'm not involved with this particular study, but you can see that there's actually enhanced resolution over northern India. And machine learning efforts. So this is, again, as I said, relatively new. We have we are collaborating with the LEAP project, and that's out of Colombia, and it is an NSF-funded Science and Technology Center. We are collaborating with M Squared Lines project that's out of NYU, and it's particularly focusing on the ocean and sea ice. We are collaborating with NVIDIA. This is more on the emulator side. They are essentially using our data sets for short-term weather prediction, and then they are being extended now. I think they are extended to climate time scales. We have some small-scale collaboration with HP using SmartSim, and all of these essentially targeting improving parameterizations, leveraging physics to improve machine learning, calibration of Earth system modeling or Earth system models, improving predictions, and advancing model evaluation. So just to give you a better idea, in particular, our collaborations are really picking up right now with LEAP and M Squared Lines. M Squared Lines was, I neglected to mention that it's funded by Schmidt Sciences. So the goal is using essentially observations, high fidelity models, in this case, we are calling CSM, and new ML algorithms. The idea is essentially to produce either new ML-based parameterizations or ML-enabled parameter optimization. And the goal is then to create a next generation CSM, and we are calling it right now CSM3 machine learning or MLE. And then the goal, the ultimate goal, is to produce more accurate projections. So just to give an example for the parameter optimization, This is particularly using the land model, that's the CLM, Community Land Model. It's a component of CESM. And then CAM, that's the Community Atmosphere Model. In the land modeling group, the goal is to generate a perturb parameter ensemble through machine learning, and it's an iterative process. I'm not familiar with this CAM one. They are essentially using adaptive Gaussian process emulators in their approach. For the parameterization side, there are a lot of sort of efforts, and this schematic is showing the contributions from the LEAP project in green, M Squared Lines project in purple, and in collaboration with ICON and E3SM, they are shown by sort of the grayish line with dash boxes. So you can see that, for example, from the ocean side, we just had actually a meeting last week about ocean model machine learning parameterizations. For the vertical mixing, that's the K-profile parameterization, there is a machine learned replacement for the shape function of the K-profile parameterization, and that's a relatively sort of easy implementation. Regarding ocean mesoscalities, this is particularly focusing on momentum fluxes. So there's a parameterization to replace momentum fluxes. And there's also a new effort replacing the bulk formulations with machine learned sort of kinematic fluxes. So this is still actually a relatively new piece of work. And in other components that I'm not familiar with, they are actually looking at sort of various land model, and on the atmospheric side, warm rain, ice microphysics, and turbulence and convection. That's also from the ocean side as well, replacements for these parameterizations. The catch here is that we need to be mindful of the cost associated with machine learning approaches. We need to essentially make sure that the advances that come about from or bias reductions are really important in ocean modeling or Earth system modeling. We need to make sure that those bias reductions are actually there with machine learning approaches, and they do not necessarily add a significant cost. Otherwise, that may create challenges for the machine learning applications. And then, as I said, I'm just repeating myself here, is the goal is
Gokhan, sorry to
essentially...
interrupt. Maybe you can wrap up in another
Yes, I'm almost there. Earth system, the bottom line is that creating through machine learning an advanced or Earth system modeling that can essentially produce produce an Earth system model with reduced systematic errors. So my final slide is essentially sort of summarizing challenges and opportunities in Earth system modeling looking ahead. In my view, workforce is a major challenge. Training of the next generation of model developers is a big challenge. There are not that many people who are interested in learning or getting into Earth system modeling. Funding remains a major challenge, especially under current circumstances in the US. Continuing development and improvements of workhorse models, in my view, is important. Advancing process understanding and Earth system predictions are also important. Enabling research using a hierarchy of models on a range of computing platforms. This can be from idealized models to process models to coarse resolution models, and all the way to high and ultra high resolution models. We need to take advantage of new emerging developments such as machine learning as the topic of this particular workshop, and rapidly expanding landscape of novel computing architectures and programming methodologies. We need to expand and maintain our diagnostic and analysis tools to support model development and evaluation. And finally, we need to co-design and co-develop models and simulations for more actionable and societally needed science. With that, I'll stop, and if you have any questions, I'll take them. Thank you.
Thanks a lot, Gokhan. Wonderful overview on Earth system modeling, starting from history, the complexities, challenges, and where we are right now. I had some questions on the ocean part, but I see that you will be taking the ocean part in the
Great.
next couple of
Yes.
lectures. But I have a before I get into the Q&A with other participants, I had a quick question on the parameterization. So we generally prepare the parameterizations based on the observed conditions and so on. So do you see these parameterizations changing over time with climate change? As conditions change, because we may not have taken into consideration the changing, the multiple elements interacting in a changing condition. What do you think?
Yes, I mean that's a concern, and because most of our evaluation and validation of parameterizations are based on existing observations, and we try to also tune our models to obtain essentially present day observations. I mean, for example, if I talk about mesoscale mixing parameterizations within the ocean component, they are tuned for sort of coarse resolution models to produce, let's say, heat transport or Antarctic circumpolar current transport for present day climate. And based on that, we are assuming that it's going to behave nicely when we go to different climates in the future.
Right.
So that is a challenge, and I don't know how to evaluate that essentially, or what else to say. It is same as, I mean, regardless of it's essentially we may be going beyond our sample size in a sense, right? Or sample area. And we are assuming that that's going to be okay in the future or out of sample things, because we are saying that the basis is physics, and if our physics is correct, it should behave the same way in the future.
Yeah, yeah. Well, thanks, Gokhan. I guess we keep improving our parameterizations as we go forward.
Yes. Yeah.
Adway, I don't see any online hands up. If you want to pick questions from those participants over there.
Yeah, so if any of you have any questions, please feel free to raise your hands. And
hello, Professor Gokhan. I
Yes.
have two questions. First question is, in community assisted model, why community term is there? That I cannot understand. And the second one is, now the AI ML is improving as the part of the R system modeling or GCM model. We have seen the Dereco supercomputer in the slide in NCR, which is a huge computation system, which has a huge computational, huge system is there. But do you feel that introduction of AI ML will reduce the computational requirement in future?
I missed the first question, but I can answer the second one. I so so far, as far as I can tell, ML and AI approaches that are being used to replace parameterizations in an online manner is actually they are costing more than the actual parameterization. For example, momentum fluxes, the parameterization seems to be adding another 5 to 10% to the model, to the existing parameterization. KPP part, as far as I can tell from the ocean side, is only adding another, I don't know, less than 5%. So they are not necessarily reducing the cost. I think the reduction in cost will come through the emulator approach, in my view. And I don't think that that is being used yet, besides, for example, forecasting purposes. So that is, I think, an important distinction. So that is one thing. And another thing is that we have a newly funded project. Actually, we are trying to convert MOM6 to run on more efficiently on GPUs. And that may essentially require certain conversions or conversions of certain parts of the code to run on C++, not in Fortran. So there are some actually advantages going to GPU-enabled systems with C++, and somehow if the machine learning part, likely emulator-wise, can be essentially incorporated in that, then there might be some gains. But retro by itself is not going to be enough for that purpose. I don't know whether I answered the question or not, but I think what I'm getting is essentially replacing parameterizations with ML by itself is, I believe, costlier than the actual parameterization.
Okay, okay.
And yeah, and then I don't know what the first part was. You
My
said
first
something
part
with,
was why it's named as community R system model. What is the community term signifies here?
oh, community is essentially, we are, as far as I know, the only Earth system model in the world which involves community participation at great extent. So all of our working groups, essentially, if somebody, for example, wants to incorporate something into the model, we do it collectively. They come and to attend one of our annual meetings or winter working group meetings. We discuss the benefits of a new approach, pros and cons. And if there's enough funding in a community, with the community, we try to bring that, for example, parameterization or some approach into the system. And the governance, all of our sort of working groups are involving community, not many as NCAR people, but more university community or laboratory community. So that's what it means, essentially.
Okay, thank you. Thank you, Professor Gokhan.
We have time for maybe one more question. Anyone?
Hi, sir. Thank
Yes.
you for the nice talk. Sir, I just wanted to know your views about reduced order models in view of parameterization, like extracting dominant structures. Uh,
Reduced order models, do you mean reduced physics
dimen-
or
no, sir, dimensionality reduction, like DMD. Uh,
well, I mean, that can be used. I mean, I think that can be beneficial. The If I understand it correctly, for example, I know that some modeling groups, such as the NEMO modeling group in the ocean modeling community, is actually using, for example, reduced order grid, coarser grid for their tracers, and then combining it with essentially physics that's running on coarser models. So that can be one approach. Another reduced order, I thought that you were asking for reduced precision. I know that some groups are trying to do that to gain speed. And and then also some cases they are using actually reduced physics also. That's another thing. Those are all applications, but I think it depends upon the science question that one is after, ultimately.
Thank you, sir.
Okay, we have one online question. So this question is that from Balakrishnan. Mostly we are using reanalysis sets to train the AI models, but these reanalyzed data sets themselves have biases and errors. So how will these AI models overcome these biases for training data sets? Any perspective on that?
Good question. Well, I mean, that is true. I don't know. First of all, uh, I'm a bit biased against reanalysis products because, especially, well, all reanalysis products are not conservative because they ingest data sets, TNS, let's say, or temperature and humidity or salinity, and just by definition, they become non-conservative and their energy imbalance is large. If you take analysis products at face value, you'll see that their energy balance at the surface is off by 30 to 40 watts per meter squared, meaning that they actually represent a different state than the climate. So I think one needs to be mindful of that. But of course, the forward models have their own biases as well. But that's what we have in a sense, right? I mean, I don't know what else to use. And AI training and ML training, they are data hungry, and they are using all they are what's available. So I'm not sure what else can be used.
I guess there are, there is progress on physics-informed AI models where they are constrained by, the physics, the conservation of mass, momentum, energy flux,
Right.
and all. Anyway, we
Right.
can. There is one more question, Gokhan, but I guess we can take up that. In the next session, next lecture.
Yeah. Yeah, so actually, we are out of time now, and it's time for the next talk. I hope many of you have various other questions, because that's the aim of this workshop, to bring out as many questions as possible. So what I suggest is you please mail me directly, and what I will do is compile the questions and communicate to Gokhan, and then I will share the response with you. So meanwhile, let's thank all of us, online and offline participants. Let's thank Gokhan for a very wonderful and insightful introduction to the Earth system models.
Thanks a lot, Gokhan. Have a good night.
No problem. Yeah, thank you very much. I'm again sorry not to be able to be there in person.
Yeah, we would love to have had you here in person. But anyway, thanks a lot for taking out the time on your Sunday night.
No problem.
See you again tomorrow.